Oh, it's 8 o'clock. Okay. So it's time to get started. Okay, let's see. Well, I think Mr. Miller is not here yet, but I think he's finished grading your homeworks and probably has returned those to you. He also sent me the homework solutions, so I will be posting those today on Blackboard. And let's see, we're going to talk more about, oops, okay. Remember to record. Okay, we're going to finish talking about related rates today, and that is on your homework, as well as, what else we've been talking about? Implicit differentiation, higher order derivatives, and okay, I threw in a couple of tangent line problems and velocity problems just because I've never given any of those to you before. But yeah, go ahead and get started on your homework. It's a little bit long, and it's not designed to be worked in one night. So get started on that so you'll have it, be able to turn it in plenty of time. Okay, any questions? All right, then let's go to the shared screen and work a couple of more related rates. Okay, so yeah, we're still talking about related rates. And here's a problem. This is the ladder problem. A ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, so again, this problem doesn't last very long because eventually the ladder hits the ground, the top does. But all right, so while it is sliding down the wall, okay, draw a picture here. The ladder is 10 feet long, and that's not changing. And that's supposed to be a vertical line there. What is changing is how far down the wall it is, and also how far the bottom of the ladder is from the wall. Okay, so let's call this X and that Y. And we want to figure out how fast the top of the ladder is sliding down the wall when the bottom of the ladder is 6 feet from the wall. Okay. And, okay, basic relationship here, Pythagorean theorem. So as long as the ladder is sliding, x squared plus y squared is equal to 10 squared. Okay, that's the relationship between x and y.
X is equal to 6.
No, the ladder, okay, the ladder is 10 feet long. Okay, 6 is a particular moment in time. Okay. But as long as the
Okay.
letter, okay. So as long as the letter is sliding down the wall, you've got this relationship. So X represents the distance from the bottom of the letter to the wall. Y represents the top of the ladder distance from the ground. Okay, so all right, somebody's in the waiting room. Okay. And I'm sharing my screen, sure enough. Okay. Okay, so that's our basic relationship. And what's the relationship between the derivatives then? Well, x is a function of t, x is changing, y is changing, y is a function of t. Somebody else. Okay. And I have to keep that in mind when I take my derivatives. Okay. So the derivative of 10 squared is 0. I'm differentiating now. And the derivative of x squared, okay, x is a function of t. It's not just a plain old variable. So I have to use a chain rule. The derivative of x squared is 2x dx dt. Likewise, y is a function. So y squared, I have to use a chain rule. The derivative of y squared is 2y dy dt. And let's see, well, I may as well divide out that 2. That basically gives me the relationship x dx dt plus y dy dt is equal to 0. And now I start putting in some other things. Let's see, what's our information here? Well, we've used the fact that the ladder is 10 feet long, but we're also given the bottom of the ladder slides away from the wall at the rate of 1 foot per second. Okay, and that's talking about dx dt. Okay, 1 foot per second. I'll leave off the units for the moment. So I know that. Let's see, what else do I know? Well, we want to find dy dt. And we're also given, okay, we want to know this at a particular moment in time, and that's when the bottom of the ladder is 6 feet from the wall. That's talking about x at a moment in time. X is 6. And we want to find out, oops, and slipped. We want dy dt. Okay, so I've got the x dt is 1 and x is 6. I want to find dy dt. I still need a value for y. How do I get a value for y? Well, I use this basic relationship. When x is 6, I've got 6 squared plus y squared is 10 squared. Okay, and this is one moment in time. Okay, but Pythagorean theorem holds for all moments in time. But we'll get y the value of y for this particular moment in time. So that says that y squared is 100 minus 36, which is 64. So y is, well, okay. If we got y squared is 64, y is generally plus or minus the square root of 64, which is plus or minus 8. But in this context, for this problem, minus 8 equal to y makes no sense. So we throw away the y equal to minus 8, and so y is equal to 8. Okay. All right, so we have x is 6 and y is 8. And we're all set to go, because now all we need to do is to figure out what dy dt is. So x is 6, the x dt is 1. Let me write the whole relationship again. And let's see, so I put in 6 for x, 1 for dx dt, and we just got that y was 8. Oops. No. And that says that 8 is minus 6, so dy dt is minus 6 over 8, which is minus 3 over 4. So dy dt, the minus means that y is decreasing, and that's true, right? Because the top of the ladder is sliding down the wall. And that distance from the ground is decreasing. Dy dt then is minus 3/4 foot per second when x is 6. Any questions? Okay, so in this problem, the basic relationship came from the Pythagorean theorem. We had another problem that had the Pythagorean theorem. The cars coming towards the intersection yesterday. But we can also, yeah, your basic relationship's going to vary. Sometimes you'll use similar triangles. If you've got a volume or an area that's changing, you need to know what the basic formula for that area or volume are. It all depends on the problem. These problems, okay, you want to read the problem carefully. Draw a diagram. I like to draw pictures. It helps a lot. Figure out what you're given, and what you want to find out, what the question's asking, and then go from there. But each problem is a little bit different, and there's no really set way to go about all of them. I thought I'd work one more. And this one is, actually, this one's out of your text. Text has some pretty good problems in it. All right, so I've got a changing angle of elevation. So here's the problem. A television camera. Oh, okay, before I do that, questions. Does anybody have questions? Okay, I'll take that as a no. So here's another problem. A television camera at ground level is filming the liftoff of a rocket. That is rising vertically according to the position equation S equal to 50t squared, where S is in feet and T is in seconds. So the time is in seconds, S, your position. So this S 50t squared is going to give you the height of the rocket at time T. Okay, and the camera is 2,000 feet from the launch pad. $2,000 feet, so that's about a half mile, a little bit less. The way those fire comes out of those rockets when they go off, I don't know if that's far enough away, but I guess that is not my concern here. Okay, so a picture. The camera is right here. Okay. And it's not moving. It's 2,000 feet away from the launch pad, which is right here. And the rocket takes off vertically and is moving up. Okay, so we have the height. Of course, this is changing. S here is changing. The 2,000 feet doesn't change, but okay, well, what's the question? Find the rate of change Rate of change means derivative in the angle of elevation. Of the camera. Okay, so the camera, well, as S changes, it's going to have to point higher, right? So that angle's changing. Theta is changing. S is changing. It's changing. And in this case, we're given how it's changing. So we're given that. Theta is also changing. So theta is a function of t. And we want to know what theta prime is. What's d theta dt? Oh, okay. I didn't finish. I didn't finish the question. 10 seconds after liftoff. It's not necessarily going to be the case that this rate of change is going to stay the same over the entire period. Maybe we'll figure that out too. After liftoff. Okay, so we want to know what happens, what's happening at the 10 seconds. That's the moment in time we're interested in. Okay, so what's the basic relationship here? Well, I can use okay. Anybody want to hazard a guess before I say something else? The Pythagorean theorem is not going to, okay, it applies here, but that's not really going to help me much because I want to know about how fast that angle is changing. But I've got a right triangle. Basically, okay, so relating the angle there to S, the tangent of theta is S over 2000, right? Opposite over adjacent. And that applies, well, not for all time t. At some point, I guess the rocket, depends on what kind of rocket it is, but maybe it escapes the Earth's gravity and it's gone someplace. But up until that time, it's just going straight up. We have this relationship. The relationship between the angle of elevation and how far up the rocket has gone. Okay, so that says that the tangent of theta, well, we're given that S of t is 50t squared. Okay, and now differentiate both sides. Well, the right-hand side's easy. It's just 50 over 2000 times 2t. What's the derivative of the left-hand side? Remembering that theta is a function of t. Theta changing. Would somebody please tell me?
It would be secant squared theta.
Okay. Times because theta is a function times d theta dt. But thank you, Mr. Levy. Okay. Well, let's go through why that d theta dt is there carefully. You've got this function. I'll just call it h of t. Remember, theta is a function of t. So the inside, this is composition, the inside function is theta of t, which we call u. The outside is the tangent of u. So h prime of t is the derivative of the outside applied to u times the derivative of the inside. Well, that's just theta prime of t. In fact, I want to know what theta prime is, but that gives us then secant squared of theta times d theta dt. Okay, so we've got this relationship between our derivatives, and d theta dt is equal to, okay, what's 50 over 2,000? Well, first of all, I can get that's 5 over 200 is 40. 5 over 200, but I can get rid of, okay, 5 over 100, which is 1/20th. Let me check my arithmetic there. Sometimes. Okay, it's 5,000, 50 times 2 over 2,000 is 50 over 1,000. Dividing out the 2 is 5 over 100 is 1 over 2. Okay, I think that's right. Okay, so d theta dt is equal to 1/20th t. And oh, wait a minute. No, I left out the secant squared altogether. Secant squared of theta. Okay, that's better. D theta dt then is, okay, secant squared is 1 over the cosine squared. So d theta dt is t over 20 times the cosine squared of theta. And that means I need the cosine. Okay, and also, what other information am I given here? I want to know about what happens at t equal to 10. Okay, I'm that far. I want to know d theta dt when t is equal to 10. Okay, this is kind of an aside. Okay, so I got a value for t that I'm going to put in. I need to know what that cosine is. Okay, so back to my triangle. if the adjacent side is 2,000 and the opposite side is 50t squared, okay, and now I'm going to use the Pythagorean theorem to get the hypotenuse. The length of the hypotenuse is 2,000 squared plus 50t squared squared. Okay, so the cosine of theta would be 2,000 over that big square root at that moment in time, okay? Well, in fact, that would hold for all moments in time when t's changing. So let's see if I can remember that. The cosine of theta is equal to that okay. Make sure I remember everything correctly here. So let's see. Okay, so now all I got to do is put in the t equal to 10. So we got that d theta dt if I screwed up my arithmetic, would somebody please say something? Okay. This is true in general. Okay. And so when t is equal to 10, we have d theta dt is 10 over 20. And then that's a 2,000. And then 2,000 squared plus, okay. T's 10, so 10 squared is 100 times 50 would be 5,000. And okay, let's see. Okay, so that's d theta dt right there. That is a number. Let's see if we can clean it up some. First of all, 10 over 20 is a half. And a half times 2,000 is 1,000. And okay, so oh, wait a minute. Wait a minute. Did I ever take DSDT? Did I ever take DSDT? Yeah, I did. Because I wrote it. Okay, that should be right. My number's not quite coming out right here, but let's see. They almost are, but must have made an error someplace. All right, that 2,000 squared plus 5,000 squared. Okay, I can factor out 1,000 squared from both of those. 2,000 squared is 2 squared times 1,000 squared. 5,000 squared is 5 squared times 1,000 squared. And that is 4 plus 25 is 29, then times 1,000 squared, which is the square root of 29 times the square root of 1,000 squared, which is the square root of 29 times 1,000. And I'm missing a 2 someplace. Okay, so I don't know where I lost it, but what I've got is 1,000 over the square root of 29. Oh. No, that's right. Times 1,000, which is 1 over the square root of 29. And I missed some arithmetic someplace because it was supposed to be 2 over 29, d theta dt. Well, I don't want to spend the whole, oh, what time is it?
Could it be because you took out the, you reduced 2,000 by half?
Yeah, okay, I took the 2,000 over 20. Oh, okay. I went wrong someplace with my arithmetic, that's for sure. So there's an error. Yeah, I don't want to waste time finding my error. But I will find it after class, okay? And I will fix it tomorrow. So yeah, I was supposed to get my arithmetic went wrong somewhere. Supposed to get, and also I'm not supposed to have that square root left in there. 2 over 29, and that's equal to d theta dt. And that would be 2 over 29 radians per second. Remember, in calculus, we measure angles in radians and not degrees. Okay, so I will find my error. Me and arithmetic don't always get along. Okay. So that's my assignment for tonight. And actually, okay, so I worked what, five related rates problems. The best thing for you all now to do is to work these problems yourself. The last last set of problems on your homework, I've got it right here. Number 8 through 14. So that's 1, 2, 3, 4, 5, 6, 7 of these. Yeah. Best thing to do will be to get started on working those and see how you come out. Okay, so that we sort of finished up our basic introduction to derivatives here. We talked about the definition of what a derivative is. And I made you use that at first, because you always have to go back to the definition, okay, when you're dealing with something new. Then we talked about the differentiation rules or differentiation laws. And now we've started using the derivative to do some things. Okay. And we're going to continue doing that. We're going to talk about, well, next, optimization. So how you find the largest point a function reaches and the smallest point a function reaches sometimes when that makes sense. And we're going to use derivatives to do that. And we're also going to use derivatives to help us graph functions. Okay. So let me tell you about two theorems that are going to be important to us. The intermediate value theorem and the extreme value theorem. And I abbreviate these IBT and EBT, and we're also going to have a mean value theorem a little bit later. But what do they say? The extreme value theorem and the intermediate value theorem don't even require that you have a derivative. Okay, so, well, let's see. Let's do the intermediate value theorem first. THM is an abbreviation for theorem. Okay, suppose f, is a function that is continuous on the closed interval. Closed interval is very important. AB, and also f of A is not equal to f of B, so it takes different values at the endpoints. Then if big C is a number I'll just say between, because I don't know whether f of A is bigger than f of B or not. Just that they're different. If C is a number between f of A and f of B, there exists some number little c in the open interval from A to B such that, I don't really need a comma there, f of little c is big C. Okay, so what is that saying? Let me draw a picture. Suppose this is my interval AB. And that's f of A and that's f of B. Okay. Well, I don't really know what the function does in between A and B. It could go up and come down and whatever, look like that. That's not a function. So it could do lots of different things. Maybe it looks like that. But if I take any number, and this is this big C, okay, any number between f of A and f of B, this theorem says that there must be some number little c, it looks like it's pretty close to A in this case, little c between A and B such that f of little c is big C. In other words, I can't go from here to here without somehow passing through every y in between. Sometimes there's more than one C. I'm not sure whether at this point they're on the same level or not. Well, it's just a picture. But sometimes there's more than one number little c that this applies to. But as long as your function is continuous, this statement is true. And okay, so we'll do some problems tomorrow using this theorem. But let me just tell you what the extreme value theorem says. The extreme value theorem says that if f is continuous on a closed interval, AB, then f attains a maximum value on AB and a minimum value on AB. So it reaches the highest point and it reaches the lowest point. Now, for this to be true, it's really important that you have these hypotheses that is satisfied. Okay, that is that f is continuous and you're only talking about a closed interval. And A and B are numbers. So, okay. And again, I don't have any idea what f is doing. What? Okay, say it. That's not really it. Okay, not even a function. Yeah, because it wouldn't pass the vertical line test. That's why that's again. Okay. So maybe f looks like this. And in my picture, it looks like the highest point would be the maximum. Okay, the highest point is f of B. And the minimum would be whatever that thing is. Okay, I'll call it X. Yeah, this is f of b. F of x, whatever that x is. Okay, so x, the lowest point and the highest point would be f of b in the picture. Yeah, so sometimes the minimum occurs at one of the endpoints. Sometimes it occurs somewhere in the interior. Both situations can happen, and likewise for the maximum. Okay, so we're gonna do some problems using the extreme value theorem. We're gonna find maximum and minimum values for some functions on closed intervals tomorrow, and we'll also do some problems that use the intermediate value theorem. But maybe I will stop there for today. I think I'm almost out of time anyway. Any questions? Y'all are awfully quiet today. Anybody got any questions? Okay, well then you can go. Okay, and I'll see you tomorrow.
Bye.
Have a good day.
I'm not sure if I'm going to be able to get on the thing tomorrow because I got to be at the school.